Good morning and welcome to this Copernicus Marine Service training workshop dedicated to the Arctic Ocean. My name is Ergan Fouché. I work at Noveltis as an ocean engineer, and I'm going to be your trainer for this practical session dedicated to Python and Jupyter notebooks. In this session, we're going to carry a study on the Arctic Ocean Thermoline Circulation. This notebook is dedicated to intermediate level users, which means that if you're not familiar with Python, NetCDF files, and Copernicus Marine Service products, you may find it difficult to go through all the notebook. However, we have designed a specific notebook dedicated to beginners, in which you will learn everything about how to access the Copernicus Marine Service products, how to manipulate them, how to see what they contain, and how to plot basic figures such as time series, vertical profiles, and maps. So if you're not familiar with this notebook, if you find this notebook too difficult, you can try to have a look at the first one, and then you should be able to go through this second one. This notebook works just like any other notebook. You will have Python code cells and text cells, and if you want to run a code cells, you can click on the button, the arrow button on the top menu here, or you can use the keyboard shortcut Shift and Enter. And in case the notebook does not work anymore, you can try to restart it by clicking on the loop arrow on the top here. So here is the program of today's session, of this video. We're going to have an introduction first on the thermohaline circulation. Then we're going to set up Python, importing the required libraries, setting up the OpenDAB solution, which we will need to access the products. And we will also have a presentation of the product we will use in this study. We're going to learn how to manipulate the coordinate systems, especially the polar stereographic north coordinate system. The first practical section will be used to understand the thermohaline circulation, to see how the vertical movements of the currents induce the horizontal currents. So we're going to compare the currents, the temperature, and the salinity. Then we're going to see in another section how the currents are affected by climate change, studying the sea ice loss in the Arctic Ocean and studying the consequences of this loss on the thermohaline currents. After the conclusion, I'm going to propose you a set of exercises for you to manipulate the Python codes that will be presented in these exercises, and to become more familiar with Python and the Copernicus Marine Service products. So, the ocean currents have a major influence on the Earth system, on climate, on weathers, because they carry the heat from the equator to the poles. We can separate these currents into two categories. We have the surface currents, which are driven by the wind, the tides, and the rotation of the Earth mainly. And we have the deep ocean currents, which is what we're going to study, which are affected by the changes in density water. These changes in density water is what induce the thermohaline circulation. So Thermo refers to the temperature, whereas haline refers to the salinity. And you may know that the temperature and the salinity have an impact on the water density. So the colder a water is, the denser it will be. And the more salty a water is, again, the denser it will be. So the vertical movements, which are due to the density difference, happen when some dense water is on top of a less dense water, and therefore the less dense water rises to the surface, and this is the vertical current that begins. So for example, when cold water is on top of hot water, the cold water sinks to the bottom of the ocean. In the same way, when some fresh water, so not salty water, is at the bottom of the ocean, then this fresh water rises to the top of the ocean, to the surface. And this is the loop that happens and that induces the thermohaline circulation. The changes in density, so the changes in temperature first, is due to several factors, which are the heat of the atmosphere and the sun radiation. And the salinity, on the other hand, depends on the input of fresh water from precipitation, river runoffs, evaporation, ice melting or freezing. And the ice freezing especially is very interesting, because when the water freezes, only the fresh water turns to ice, and therefore it leaves the salt behind. So when the water is freezing, the water below becomes more salty and therefore denser. This is how the thermohaline circulation begins, and therefore the Arctic and Antarctic Ocean work like a pump, which feeds the thermohaline circulation. In the frame of climate change, you probably know that you have fewer and fewer ice concentration in the Arctic Ocean, and therefore the changes in density are not as high as they used to be, and therefore we can observe, or at least we begin to observe, that the thermohaline circulation is beginning to slow down, and some scientists are worried it may stop. We still don't know the consequences of such change. We don't know what would happen if the thermohaline circulation slowed too fast or if it stopped. But studying and understanding the oceans and their currents is crucial to forecast the effects of such change and to prepare to these consequences. So this is what the Copernicus Marine Service is dedicated to, studying and understanding the oceans. And in this notebook, we're going to see several tools, several Python codes, in order to visualize and study the thermohaline circulation and see how it evolves and how it has evolved over the last years. So let's start to use Python. Just like any other Python code, we need to initialize the environment by importing the libraries. So here is the list of the libraries we're going to use. We're going to use NumPy, which is a fundamental package for scientific computing, very basic library. We're going to use Xarray, which is the library we use to manipulate NetDF files within Python. We're going to use Matplotlib to produce the figures in Python, and we're going to use Cartopy, which is the library that we use for maps and geospatial data analysis. This cell imports all the required libraries. And so now we're all set up to begin the exercise. If you have been through the first notebook, the one dedicated to beginners, you have seen that you don't have to download the files that you want to study. You don't have to download the products. You can use the OpenDAP solution to stream the product, to use it without downloading it. And in order to do this, you just have to run this cell. And if this is the first time you run the cell, you may have to enter your credentials. In the rest of the notebook, we're going to use either the products that have been downloaded, which are, by the way, stored in the data folder of the notebook. You can see these are NetDF files. And we're also going to use the products from the OpenDAP service. So you can choose either to stream the products or to download or to use the ones that are already downloaded. So talking about the product we are using, here is a brief presentation of it. So we're using the Arctic Ocean Physics Reanalysis model. You can have a look at its documentation page here. This is going to open the catalog web page of the product. So you can have all the information of the product. You have the spatial resolution, the temporal coverage, the temporal resolution, and many more. You have the variables that are computed in the model, and you also have a small description. And this is also how you can access the product if you click here on data access, etc. But I don't want to spend too much time on it, because if you have a look at the first notebook, everything will be explained. Oops. So the variables that we are going to use here are the temperature, the salinity, the velocity, and also the sea ice thickness that is also included in the product. You may have seen that you have several temporal resolutions included in this model. We are going to consider monthly means, and we're going to use it from 1991 to 2020. We're going to consider all the depths, so from minus 5,000 meters to the surface, the 0 meters. If you need to find information on the product, you can have a look at the product user manual and also the quality information documents. All these links will lead you to the document, which will explain you the information on the product. So that's it for the introduction and the presentation of Python and the product we need. We will begin to talk technically, and we'll start with the coordinate system. So in the first notebook, if you have had a look at it, we have plotted this figure, which shows the difference between the polar grids, so in the geographic north coordinate system, and the global grid, which is used in the global models and in most products in the Copernicus Marine Service, in which the coordinates are the latitude and longitude. Here you can see that we have the coordinates are the x and y, and this is because if you look closely here, you can see that the latitude longitude system is not relevant because you have plenty of points in the highest latitudes, whereas in the lowest latitudes the number of points is sparser. So the x and y coordinate system, which is the polar stereographic north coordinate system, is more relevant than the other one in the poles, in the Arctic Ocean especially, because the number of observation does not depend on the latitude. In Python and in this notebook, we're going to use Cartopy, the library I've introduced to you before. And there are two parameters that you're going to need and to understand if you want to be able to plot the maps. The first one is the projection argument, which determines the projection of the map. So this has nothing to do with the product you're using, it just depends on what kind of map you want to create. In the first notebook again, we have presented several ways to display a map depending on the projection. The second argument is the transform argument, which tells the library Cartopy what coordinate system our dataset uses. So the transform, in the transform, for example, will you have to set the transform argument to tell whether your dataset uses this coordinate system or this one. This is an example. If you want to have a look at the projections that are available, you can have a look at the Cartopy documentation. Here you will have the list of the projections that are available. So you can see you have plenty of ways to display maps. And if we go back to the web page of our product, you can see that you have the description of the coordinate system, and here you will see that it's polar stereographic north. This means that it's x and y coordinates. You have understood. In order to tell Cartopy which precise transform argument to use, we are going to plot the x and y coordinates, the x and y axis on a grid, and to do so we will open a model. So this is the model that we are using, and we are going to open it for once with OpenDAP. So we just run the cell. We are using the OpenDAP dataset function, and instead of putting the path to the file, we just put the link to the OpenDAP web page. Then we check on the products variable, and you can see that indeed the dimensions of the products are depth, time, and x and y. Latitude and longitudes are only coordinates which depend on x and y, but they are not dimensions. So in this cell we are going to plot the x and y axis. So we select the axis where x equals to 0 and the axis where y equals to 0. Then we plot a map. So here we're using the projection that is entitled North Polar Stereo. And here are the lines that define the characteristics of the map. So we add the coastlines, the grid lines. We remove the labels. We add the landmass, but we're probably not going to see it now. And we set the extent. So we focus, well, the lowest latitude will be of 85 degrees. Then we use the scatter, the matplotlib scatter method to plot the x-axis and the y-axis, and then we plot the legend. So let's run this cell. And here is the result. So the x-axis in blue goes in this direction, whereas the y-axis goes in this direction. From this plot, well, the Cartopy transform argument we're going to use is the stereographic one. So if you have a look at this, at the documentation here, you will see that we need to tell what is the central latitude. So here, we can see, we can see that it's centered on the highest latitude, so on 90 degrees. And we also need to set the central longitude, which is here, minus 45 degrees. If we have a look at the x attributes, so here, show height attributes, you can see that the units of the x-axis and also of the y-axis are 100 kilometers. Therefore, the last argument we will use, so that we set the central latitude, the central longitude, and we also apply a scale factor in order to put our data set in meters and not in hundreds of kilometers. So we have set our transform arguments, and we are now all set to study the thermohaline circulation and to use Python with our dataset. I understand the projection and transform arguments are not very easy to understand, but I'll try to be very clear in the following maps for you to understand which argument you have to use in which case. So let's begin the study of the thermoline circulation. We have seen in the introduction that the thermohaline circulation begins with changes in temperature and salinity. This is what thermohaline means. Therefore, in this section, we're going to compare a map of the currents, of the temperature, and of the salinity. We're going to select one date and one depth, and we are going to see how, well, if we can compare the current maps to the temperature and salinity maps. So to do so, we're going to open a dataset that has already been downloaded. In the data folder here, it's called MarineData4Arctic 2020. So this dataset contains all the monthly means for the years 2020. So we open it and we see what it contains. So it also contains all the depths. So if you click here, you can see it goes from 0 to 4,000. And the times go from January 2020 to December 2020. And you have monthly means, one value per month. We can have a look as well as what the variables are. So you have here, if you check, you have the temperature, you have the salinity, You have the seawater velocity in the x direction and the seawater velocity in the y direction. So we select a depth. So let's say, for example, 500 meters. We select a depth, a date, sorry. So let's take February 2020. And then we select our product. We subset it, selecting the nearest date to the one we have set, and selecting the nearest depth to the one we have set. So we create a new variable, which will be our product at the depth and date we have set. Then we compute the current, because as you can see, you don't have the current velocities, you only have its component in the x and y direction, so we need to calculate the speeds. So this is what this line does. And then we can begin to plot our maps. In this line, we define the number of subplots. So we were going to have 3 subplots, 3 maps. We define the size of the figure, and we define the projection. So the projection here, as a reminder, is tells Cartopy how we want the map to look. It has nothing to do with our dataset. As you can see, the central latitude is not 90 and the central longitude is not -45. This is what we choose to display. Then we define again the characteristics of the plot. We have the coastlines, the grid lines, the land mass, and we set the extent. Then we can begin to plot our variables. On the first axis, the first subplot, we use the p-color mesh to plot the current velocities. We set the color map. We define the min and max values of the color map, and we use the transform parameter. Here, because we are using the longitude and latitude, we can use the plate carré transform argument. However, here we're going to plot the arrows, so the vectors that represent the current direction. And if you remember, in the product variable we have the direction in x and y direction, so we cannot use we don't have the direction in the lat and long direction, sorry. This is why we need to use the transform argument we have said before, because we are going to tell we're going to plot the vectors, so telling the x and y dimensions, then plotting then using the direction in the x, the variable in the x direction, and then the variable in the y direction. Then we set these parameters define the shape of the arrow, and finally we use the transform. But it's very important to understand why we don't use the same transform argument here. It's because we are using x and y dimensions, whereas here we're using longitude and latitude coordinates. Very important. Another parameter we're using here is the step arrows parameters that we have set to 8 here, and it reduces the number of arrows that are going to be displayed. Then we plot the temperature. Again, we use the p-color mesh with the coordinates longitude, latitude, so we don't have to use the stereo transform argument. We can use the plate carré one. Then we plot the salinity on the third subplot. Then we add the titles to each subplot, we add the color bars, and finally we save the figures. So here is the result. Oops, I have not run it. So the depth that we have chosen is displayed, the date as well is displayed, and you have the map of the currents with the direction, well, the velocities that are represented by the background color, and the arrows that represent the current direction. On the second subplot we have the temperature, and on the last one we have the salinity. What we can see is that the patterns of the current, temperature, and salinity are very similar, especially if you have a look at the pattern here on the south of Iceland, southwest of Iceland. You can see that you have the current, you have the temperature, and you have the salinity, which all look the same. And this is one proof that the currents are linked to the temperature and the salinity. So this is the horizontal current. What we are going to see now is how these currents are induced, and the answer is by vertical currents, by the changes in water density, which make denser, and so when denser water is on top of less dense water, this is how the vertical currents from the thermohaline circulation is created. This is what we're going to study now. So we are going to use again the variable that we have defined. If you check the variables here, you will see that it contains all the depths and all the months of 2020. And what we're going to do now is create a line and plot a vertical slice of the parameters, so the temperature and salinity parameters along this line, and considering all the depths, and then create an animation to see how the parameters have evolved over the 12 months of the year 2020. So first we set the coordinates of the line. We set it in the X and Y coordinates because it's easier. Then we will create a loop over the months of the product, of the data set we have. And so for each date in the product, we are going to select the model at this date and along this line. Here we convert the date to strings in order to put this date in the title. Then we define the characteristics of the plot. The lines that may be interesting, except the labels, is that here if you uncomment this line, you will set the y limits, well, the limits of the y-axis, and this line inverts the direction of the y-axis in order to have the surface on the top. Then we plot the parameters. So on the first subplot, we plot the salinity, and on the second one, we plot the temperature. We set min and max values for the two parameters in order to have the same color bar, the same legend on all the figures referring to all the months that we're going to study. Here we add the titles and the legend. And finally, we are adding a minimap on the top. I'm going to show you an example of the results here. Here is one of the results that we're going to have. So the lines that I was presenting to you show this minimap. So they show the location of the line we are studying. So we are then saving all the figures in the out animation slice cell temp folder, and then we close it. And this is why even if you run this cell, you won't nothing will be displayed, because otherwise there would be too many figures. Let's run it anyway. You will see that you have a comment which tells you when the figure is generated. Here you can see in the out folder your figures being created, and you can check on the results here. When all your figures are created, we can begin to create our animation, which has been, well, the ways to create an animation has been again presented in the first notebook, but you just have to run this cell. Oops. And you will see the animation, the evolution of the salinity and the temperature over all the months of 2020. So this animation works really well to understand how the thermohaline circulation begins, because from January here you can see the layer from the top dropping into the bottom ocean. Here you can see, and you can see as well that the temperature follows the same way. And this is this line. Well, the evolution along this line is very interesting. So the low salinity on the surface is due to the sea ice melting, and the temperature surface increasing is due, here for example, is due to the solar radiation. In summer the surface warms, and that's it. Now that we have understood the thermohaline circulation, how it begins, how the currents are correlated with the temperature and the salinity, how the changes in density induce the thermohaline circulation, we are now going to study how the thermohaline circulation has evolved in the frame of climate change. As we have said before, the reanalysis, the Arctic Ocean physics reanalysis model contains values from 1991 to 2020. So this is a 30-year-long time range, which is going to be very useful to carry such analysis at the scale of climate. So the first thing that you probably know is that the sea ice in the Arctic Ocean is decreasing at a rate that is very concerning. And this is what we are going to visualize now. So the sea ice loss prevents the thermohaline circulation because because the ice, as I have explained before, the water freezing is responsible for the changes in salinity, among other parameters, of course, but this is one of the parameters that influence the salinity changes, and therefore the density changes, and therefore the thermohaline circulation. So here we are going to open a data set which is called ice thickness in the data folder. Again, this dataset has been downloaded from the Arctic Ocean reanalysis physics model. It contains only one depth because the ice thickness is only at the surface, but it contains all the dates, all the months, so from 1991 to 2020, and it covers all the Arctic Ocean. So let's open it and see what it contains. Sorry. So we can see that we have all the time dates, and we can see that we have the parameters that refers to the sea ice thickness here. In this section, we're going to compare the ice thickness in summer, and we're going to consider two periods, so the one from 1991 to 2010 and the one from 2010 to 2020. So the first step to do this is to select from our product, which contains all the months of all the years. We're going to select only the summer months, so July, August, and September, which are the months 7, 8, and 9. And this is what this line does. We use the where method from X-array to select only the months, which are 7, 8, and 9, July, August, and September. So let's see the results. If we have a look at the time now, you can see that you only have July, August, and September months for all the years, but you don't have the months from the other seasons. Oops. The next step for our analysis is to calculate the mean sea ice thickness, so in summer still, but for the two periods that we're considering. So here we are selecting the times from 1990 to 2010, and in the second dataset we are going to select the dates from 2010 to 2020, and then we apply a mean to calculate the average sea ice thickness in summer over this period. Let's see the results. You can see you no longer have the time variable because you have applied a mean on this dimension. So you only have the sea ice thickness all over the Arctic Ocean, but for no depth and no time. In this code cell, we will plot the two maps, so the sea ice thickness for the first period and for the second one, and see the result. Again, we are using the P-color mesh method, and this cell is not very different from the other one, so you should understand everything. So this is the result. On the left, you have the sea ice thickness in summer from the average for summers 1990 to 2010, and on the right, in summer for 2010 to 2020. What you can see, it's kind of obvious, is that the average sea ice thickness has decreased, especially you can see it very clearly in this region and in all the Siberian shelf here. It's very obvious. So this is qualitative estimation of the sea ice thickness. We can see from these maps that it has decreased over the years from 1990. What we're going to do next is to try to estimate the sea ice volume that we have lost between these two periods. The information we need to know is that the spatial resolution of the model is 12.5 kilometers square, well, 12.5 per 12.5 kilometers square. And so the method we're using to calculate the volume is that we're going to count the sum of the ice thickness in these two maps. So we're going to calculate the sum of all these meters to have the sum of the sea ice thickness, and we're going to multiply this sum per the area of one cell of the model, and then we're going to have a volume. So here is how to do it. We use the dot sum X-array method. If you click here, you will have the documentation page of this method. And we multiply it per this coefficient in order to have it in kilometers and not in meters. And then we'll multiply it by the area of a cell of the model. So we calculate the volume for the first period and the volume for the second period. We also calculate the difference between these two volumes that we have calculated, and we'll also calculate the rate of the loss, so the loss divided by the initial volume, and we have this result in %. Then we plot it on a bar chart, which we will see later, and then we print the result in order to have a synthetic sentence. So the Arctic Ocean average sea ice volume was of cubic meters on average in the summer months of 1991 to 2010, and the same in 2010 to 2020. This corresponds to a loss of cubic meters, which means % of the average volume in 1990 to 2010. Here is the result. So you have the sentence and you also have the bar chart. So this figure, I think, is much more comprehensive and much more easy to read and to consider than the maps. We can see that almost 12,000 cubic kilometers on average have disappeared in the summer months of in the period 2010 to 2020 compared to the first period. No. We can see that in the first period we had almost 12 cubic kilometers on average, and we only had 9 in the second period. This corresponds to a loss of 2,000 cubic kilometers, which is 20% of the average volume of the first period. So I think this figure help us realize easier than the previous maps how dramatic the consequences of the climate change are. So with less sea ice in the Arctic Ocean, we also have less input of cold and fresh water. And we're going to see how this evolution affects the thermohaline currents. So we're going to study a small region. The next analysis we're going to carry is going to study a small region of the Arctic Ocean on the west of the east coast of the Greenland, which is, if we remember from before, it's one of the regions where the currents were the current velocities were the highest. Here, And we're going to consider all the depths and all the time range in this small region. But first, let's have a look at the region we are studying. So this is the region. This maps is only useful to see the region we're considering. And then we're going to plot the time series to see how the parameters have evolved over the 30 years. So we are going to compute an average on all the region and on all the depths in order to have single values, one value for each parameter per month. So this is what this first line does. We calculate the mean on the x, y, and depth dimensions. Just like before, we calculate the... I think I forgot to run this cell, sorry. We calculate the salinity. Well, we just select the salinity and the temperature from the average dataset we have done. And then we can plot the time series. So just like before, we define the characteristics of the plot. And then we use the dot plot function from matplotlib to plot the temperature, the salinity, and the currents. Sorry. Oops, I forgot to run the previous cell. And here is the result. What we can see is that the temperature is undeniably increasing in the Arctic Ocean. So this is very easy to read. The salinity, however, follows a tendency, seems to be increasing, but what's interesting is that the amplitudes in the salinity, so the difference between the min and max values of the salinity, which correspond to the seasonal variation of the salinity, well, the amplitudes used to be very, very high, so we had very low minimums and very high maximums, whereas in the most recent years, the min and max values were much closer to each other. So this is an effect of the sea ice loss, because with less and less sea ice in the ocean, we have the phenomenon of ice freezing and melting is diminished. And finally, the last plot, which represents the currents, also seems to be decreasing, but it's not as obvious as in the previous plots, so for the temperature and the salinity. What we're going to do now is to calculate the rate of evolution of these parameters. So for the temperature and for the velocity, to see at what speed the temperature are increasing and at what speed the current velocities are decreasing. To do so, we're using a new library from the SciPy, which is called stats. And we are carrying a linear regression on the temperature and on the currents. And the parameters that we are going to get is the slope. These are the parameters that we are going to be interested in. And finally, just like we did before, we will print the results. So the sentence from 1991 and in the studied region, the sea temperature has increased of every 10 years and the currents have decreased of every 10 years. So let's have a look at the results. So the temperature is increasing of 0.03 Celsius degrees every 10 years, and the currents, well, the rate at which the currents are decreasing seems to be very, very low. So this confirms that the currents are the currents velocities are decreasing. However, this decrease seems to be rather slow. And however, the sea temperature is increasing very fast in the studied region. So this is the end of the Python of this notebook. We have seen how the thermohaline circulation works in the Arctic Ocean. We have manipulated the coordinate systems. We have studied the changes in seawater density, and we have seen their impact on horizontal and vertical currents. We have analyzed the evolution of the sea ice thickness and its impact on the salinity, temperature, and current velocities. And so this notebook has shown you plenty of examples of Python code to monitor the thermohaline circulation. However, this is not a scientific paper yet, at least. And if you are interested in publishing any paper or carrying any analysis on the subject we have presented here, feel free to reuse these codes. This is what they have been created for. Finally, here is a set of exercises. We have divided them into 3 categories. So you have the exercises dedicated to beginners, intermediate level users, and to experts. So the one for beginners, in this section, you can change the depth that we are studying, and you can change the date. So these are very easy changes to make, but you will create other maps, and maybe you will see some other patterns and see if the parameters are still correlated. Oops. In this section, we have defined a line which is very coastal, or very near to the coast of the Greenland, and so the phenomena that occur in this region are not the same as in the region with no land nearby, because we have some inputs of fresh water coming from the land, which we don't have elsewhere. So if you change the location of the line, you may see other interesting thing. Sorry. And in this section, we have studied the summer months. But if you change these parameters, you can try to study maybe another month only, or another season, and see if you observe the same trends. For the exercises dedicated to intermediate level users, you can try to change the projection of the maps here using the section in which I explained the different projection that you can use. In this section, we have calculated, we have used the sea ice thickness parameter. However, I have downloaded for you a dataset which contains the snow thickness, still coming from the same model product. And if you have a look at if instead of the sea ice here you plot the snow thickness, you shall find even more dramatic results depending on the periods you're studying. So I encourage you to do this study, because it's even more concerning than for the sea ice. In this section, we have studied this region, but just the same as for the vertical slice. If you have a look at another region in the highest latitudes, for example, and further from the coast, you may find some different results. And finally, the 2 exercises dedicated to experts. In the Ocean State Report, which is a publication from the Copernicus Marine Service and Mercator Ocean International, you will find a map of the sea ice extent instead of the sea ice thickness that we have used. And you can try to reuse... which page is it? Sorry. You can have a look at this map, which shows the difference between the average from 1993 to 2014 and in September, and the average in September 2020. You can try to reproduce these maps. You have all the tools necessary, all the functions that you shall need have already been presented to you, so you should be able to do this by now. And finally, the last exercise I propose to you is to study some other parameters, because the thermohaline circulation does not only transport fresh and salt water, but it also carries nutrients. And you can try to compare the trajectories of the whales, for example, during their migrations. You can try to compare this migration and these trajectories to the currents. And so the nutrients, you can find them in the Arctic Ocean biogeochemistry reanalysis model, and I'd be very interested to see what you observed. So congratulations, and thank you very much for watching this the whole video. I really hope you enjoyed this second Jupyter Notebook on the Arctic Ocean. Feel free again to reuse all the content, all the material we have developed in these two notebooks, in the first one and the second one, to adapt it to your needs. And if you have any question either on the code or on the exercises, you can contact us at this email address, and we will be very happy to answer to your questions. So thank you very much again for watching this video, and I hope I'll see you soon. Bye.